We present DualConvMesh-Net, a deep hierarchical convolutional network over 3D meshes which combines geodesic and Euclidean convolutions. We perform semantic segmentation on 3D scenes. As input, we use 3D meshes including RGB color and normal information, and our goal is to assign semantic labels to vertices. Previous works limit themselves to a single 3D data representation. They either work on a voxelized representation, on point clouds, or on meshes. Each one of them comes with its own neighborhood notion on which convolutions are performed. In contrast to related work, our DualConvMesh-Net combines convolutions on neighborhoods defined over the Euclidean proximity of vertices and neighborhoods defined over the adjacent mesh neighbors. We believe that each notion comes with its own merits. Intuitively, Euclidean neighborhoods are well suited for learning the interaction between disconnected parts of the scene. Here, for example, we see that the receptive field of the green center vertex enlarges over both vertices of the share and the table when Euclidean convolutions are used. In contrast to Euclidean convolutions, geodesic convolutions follow the surface of the mesh. Here we want to explicitly learn shape inherent features of objects without fusing information of nearby objects. As both convolution types have their merits, in our DualConvMesh-Net we combine them and experimentally show that this results in overall improved performance. Our architecture is inspired by the well-known U-Net architecture for 2D semantic segmentation. We follow the same symmetrical encoder-decoder architecture with additional skip connections interconnecting the same mesh levels of the encoder and decoder. Dual convolutions enable us to learn geodesic and Euclidean features in a parallel manner while enlarging the receptive field in both domains simultaneously. We furthermore define pooling and unpooling operators in order to learn features at different scales. Next, we take a closer look into the main components of our architecture. The dual convolution module performs convolutions in two domains jointly. After calculating Euclidean and geodesic features, we simply concatenate them and pass them to the subsequent dual convolution module. Additionally, we present a novel pooling operator for changing the resolution level of the mesh while keeping track of the vertex interconnectivity. Mesh levels are linked via pooling trace maps, defining which vertices are pooled together. For pooling, we use permutation invariant functions for obtaining representative features from a set of arbitrarily many vertices. For unpooling, we simply copy features back to the original vertices. Our pooling method needs to preserve a valid mesh structure in all mesh levels, such that geodesic convolutions are also applicable in subsequent levels. We leverage vertex clustering and quadratic error metrics as two well-established mesh simplification algorithms from the geometry processing domain. To summarize, we've presented the dual convolution module, which performs convolutions in the Euclidean and geodesic space jointly. Additionally, we have introduced novel pooling operators for mesh-centric pooling, where we leverage mesh simplification algorithms. In the Ablation study, we experimentally proved the validity of the proposed dual convolution module. For experimentally evaluating our DCM-Net, we introduced two models. As already outlined, the dual convolution module operates in the Euclidean and geodesic domain simultaneously, whereas the single convolution module works either in the Euclidean or in the geodesic domain. We thus end up with two distinct architectures we used in our Ablation study. We evaluate the performance gains when combining Euclidean and geodesic information in our DCM-Net, compared to only operating in a single domain. We conduct experiments on the ScanNet v2 validation set and report mean IOU scores. In all experiments, we use mesh simplification with quadratic error metrics. Only operating in the geodesic domain yields a score of 56.8%. Whereas operating only in the Euclidean domain gains 4.1% mean IOU. However, combining geodesic and Euclidean information in our dual architecture yields an overall improved score of 62.9, which outperforms single architectures by a significant margin. Conducting the same experiments with radius neighborhoods, we yield even better results. In our paper, we provide additional studies about various mesh simplification algorithms as means of pooling. Thank you for watching.